tandem repeats rather than longer amounts, and the shorter the better. The reason why is that larger repeats are more easily damaged. I mean, there's an old saying: the longer the rope, the faster the break. If you have a small little rope, it's not going to break that much. If you use large ropes, some wear and tear somewhere on the rope is going to break. If it's a small rope, there's not much of a place for the wear and tear to make it break. So the longer the rope, the shorter the break. Same thing with DNA. The longer the repeat, the more of a chance that somewhere in the repeat something is broken. So we like to have short tandem. The shorter the better. Larger ones are easily damaged. Also, it's harder to replicate the larger repeats. I mean, you got more to repeat. You got to have more to replicate. So we like the short ones. As mentioned, when we put it through the gel or capillary electrophoresis, the higher mass, the ones that have more blocks in the given SDR. Remember, let's say this is the SDR. If it has 4, that won't go very far. If it has 12, it'll go very far. It's a curiosity. That's just the way the gel electrophoresis and capillary electrophoresis goes. It has to do with the charges on them. The bigger it is, the more charges, the more farther it'll go. That's just the idea. So someone with 17 of them will go very far. Someone with only 4 will not go very far. This is a form of chromatography. This is what the DNA profile of any sample would be. So if they take DNA from you, they'll get something that looks like this. These are again, we're not going to go through all of these numbers. That has to do with I think the genes. Never mind these numbers. That we're not going to talk about at all. These codes, what it looks like, the D8S1179. That's just the name of the short tandem repeat. D21S11 and whatever. But the point is that this short tandem repeat ended up with peaks over here and over here. There are usually 2 of them because they come from 2 different parents, and each short tandem, so we get a signal from each parent. Once in a while, you can find that each parent had the same one, so you only find 1 peak, like let's say this one. Anyway, you're going to see some of like a double peak for each one. In this case, this came over here, and that came over there. For this short tandem repeat, 1 came here and 1 came there. Now, in a different person, you won't have 1 here and 1 here. You'll have 1 here and 1 here, or maybe 1 here and 1 here, or maybe here and 1 really close over there. They're going to be different. So roughly, here's the very rough. It's a little bit rough, estimation of how it works. Let's say there's a 1 in 10 chance that 2 random people will have this STR coming out of this. It's both parents coming out of the same exact place. In other words, in this case, let's say let me just compare it to. It's not easy to compare. Okay, let's just take a look at this and this. Let's say here, this one comes pretty close to that, and these are a little farther out. I mean, just imagining that, like this is like close to the edge, and these are farther away from the edge. It doesn't really work like that, but I just want to illustrate the idea. If this is coming out farther from the edge, that means there must be more of these, more blocks in this single SDR. If this is like really close to the edge, that means there aren't that many blocks in this STR. If there would be a lot of blocks in this SDR, it would have ended up, let's say, further out, like this. Okay, it's not true because this is apparently on 1 single gel electrophoresis column, but that's the idea. The further away it is from the starting point, the more blocks there are in that specific STR. So if we find someone that has, let's say, their SDRs come out over here, and someone else has come out over there, that second person's over here probably would have had more blocks to this STR. And since different people have different blocks for each SDR, each person will have a different peak profile. Again, let's say there's a 1 in 10 chance that 2 people have the same peak profile. Okay, usually it's a little bit less than that, but let's go with a 1 in 10. Well, that's true for this SDR. Let's say there's also a 1 in 10 chance that person would also have the same retention profile as this other SDR. That's a 1 in 100 chance. And for this one, coming the same way, again, that would be 1 in 1,000. You keep this up. If you now, the profile might be the same for 1 or 2 or 3, let's say of them, but it's not going to be the same. If it's a different person, it's not going to be the same for all 16. For that to happen, it's the math over here as we as done over here. Again, assuming it's 1 out of 10. That's again a very generalization. It's an underestimate of how improbable. But anyway, so even if it's a 1 in 10 for each, for all 16 of them to be the same, you would have a 1 out of 100 trillion chance. And knowing that there's only there's less than 10 billion people in the world, it's almost we will not assume that someone randomly has the same DNA as the let's say the DNA found at the crime scene. So if we find DNA at a crime scene and we go to a person and we see his profile of all these STRs are exactly the same, we're not going to assume that, oh yes, someone out there had the same one. That didn't happen. It is we can be certain that it was the same person's DNA. The reason that all these match is that it comes from the same source. This is what is behind identifying a person using DNA. That we take all these STRs, we put them through the gel electrophoresis, we replicate them and everything, we put them through the gel electrophoresis, and we get this profile. We take it of a suspect, or we look at it's called a CODIS. We look at a database that has millions of these on file, millions of these DNA profiles on file. If our DNA at the crime scene matches one of those, then we know that at our crime scene, the one who deposited the DNA was that same person that was found in the database called the CODIS. CODIS for CO's combined, D is for DNA, S identification system. So anyway, that is what DNA is, and how it's used to prove prove a connection, to form a connection between some DNA found at a crime scene, between DNA found somewhere else. So a bit of a review. You should know what DNA is made of, the deoxyribose, the phosphates, the base group, the base pairs. Also know about PCR, how it replicates, know what STRs are, the short tandem repeats, and how and why it actually does identify a single person, why it is an individual characteristic. For those with a textbook and who want to practice, they can do these homework problems for practice.